So today we will derive the transforms of derivatives and integrals. So this type of information is necessary to find the solutions of the ordinary differential equations. So, for example, now we know that the Laplace transform of, say, 1 is 1 over s, okay, and for example also the Laplace transform of cosine of omega t is equal to s over s square plus a square, and so on, we know certain, but these are the functions. So how about the Laplace transform of the derivative of a function? Okay, so for example, f is a function t and its derivative is f prime. What is its Laplace transform? So its Laplace transform then we can find by this integral f prime dt. Okay, f prime dt. So this integral can be expanded by integration by parts. So for example, if I use the di method for the integration by parts, so then it will be e power minus st, and it will be minus e minus s e power minus st is the derivative. For f prime, the integral will be f. Okay, so plus minus so it will be e power minus st times this function of t. Okay, and the limits are infinity to 0 to infinity, and then it will be minus minus plus integral, this will be s, and then infinity, and then it will be e power minus st into f of t dt. So now we can simplify it by considering that its infinity term will raise it to will make this function as 0, because we know that this is 0. E power minus infinity is 0. How about f of t? We don't know. For example, even if we take a very increasing function of f, but the Laplace transform is only valid or identified for those functions which do not increase very rapidly. Okay, so this means that f of infinity we cannot expect to increase very rapidly. So therefore this term will be 0, and then this term will be not much high. Okay, so any term which is not much high times 0 will be 0, so this will be 0, and then for 0 it will be e power minus 0 that will be 1 times, and then it will be any function evaluated at t is equal to 0. So this will essentially become minus f0 over here, and then this is actually the Laplace of f prime function f. So this is by definition we can say that it's the Laplace of function f. So it will be L s Laplace of f of t. Okay, Laplace of f of t. So here we have the Laplace of f prime. So in this case now we can see that we have readily found the formula for the Laplace of f prime. F prime is equal to s times Laplace of f. Okay, we can write it like Laplace of f minus f of 0. Okay, so this is the Laplace transform of the first derivative of a function. How about for the second derivative? So by this if we can use this relationship, so the Laplace transform of second derivative will be equal to s times, because in this case here is f prime and here it is f. So from f prime we get f by integration. So from f double prime, we will, by integration we will get f prime. So it will be s times it will be s times the Laplace of f prime, okay, by this induction, okay. And then minus, if it was L of if it was Laplace of f, it was f of 0, so it will be over here it will be f prime of 0 by the same analogy, okay. So in this case now s and then L, now we can input the value of Laplace of f prime is equal to s into Laplace of f minus f of 0 minus f prime of 0. So it means that it will be s square Laplace of f minus f of 0 minus f prime of 0. So for the second derivative function, the Laplace is given by this function, okay. Similarly we can expand it to the third derivative in the same manner. So it will be s cube Laplace of f minus s into so it should be s over here, right? Yeah, s cube, it will be minus s square, it will be then f of naught, and then it will be minus s f prime of naught, and then it will be minus f double prime of naught as the last term. So by the same thing we can keep expanding it for the fourth and fifth and sixth or nth Laplace. So with this derivation, let's see one application of this derivation. Okay, so for example, if we have a function t sine omega t, and we want to find its Laplace, okay. So at present we don't have any such formula in which we can have can find its Laplace. So for example, t and then multiplied by sine omega t. So if we have sine omega t multiplied by e power at, then we have the s shifting theorem, but for this we don't have any formula. So for this purpose, I think what we will do is we will use the derivative theorem, and then the trick will work. So f prime of t will be equal to in this case omega t cosine omega t plus sine omega t, okay. In this case f prime of 0 will be 0, this is 0, this is 0, that will be 0, and then we can calculate f double prime of t also, so which will be minus t omega square sine omega t, and then plus omega cosine omega t, and then it will be omega cosine omega t. So in this way it will be 2 omega cosine omega t minus t omega square sine omega t. Okay, so here what we can do is, now we can, let's take the Laplace of both sides. Laplace of f prime, f double prime will be equal to the Laplace of this term. So what will be the Laplace of this term? For this we have 2 omega is a constant, and the Laplace of cosine omega t, we already know that it is s over s square plus omega square, okay. And then for this term we can take omega square as common outside, and then we can represent that this is the Laplace of t times sine omega t, but t times sine omega t is our initial function, so we can simply say that it is the Laplace of f of t. Okay, so and on the other hand, from the theorem of second Laplace, we know that Laplace of f second f double prime is equal to s square of the Laplace of f minus sf0 minus f prime 0. F prime 0 was 0. Okay, and what is f0? F0 is also 0, because from here if we put 0 over here it will be 0. So these two terms are 0. So that means this is equal to s square Laplace of f. Okay, so now we have these two. We can represent this like this. So for example, if I take this Laplace of f on the other side, so it will be s square plus omega square Laplace of f of t and f is same, and then it will be 2 omega s over s square plus omega square, so which will give us the Laplace of f in this case will be equal to 2 omega s over s square plus omega square. I will take on the other side s square plus omega square. So in this way we can find that the Laplace of this t sine omega t is equal to 2 omega s over s square plus omega square. So we have derived one relationship for the Laplace. Okay, so now let's take another example. Suppose that we don't know the Laplace transform of sine of omega t. Okay, although we have already derived it before, but suppose we don't know. Okay, so in this case, if we want to derive it by the Laplace transform of the derivatives, so what we can do is we can take the derivative of this. It will be omega cosine omega t, and then second derivative it will be minus omega square sine omega t. So f of 0 is 0 in this case, and f prime of 0 is, in this case, it's omega. Okay, and now we know that the Laplace of f prime is equal to s square Laplace of f. Okay, and then minus f of 0, which is 0, and then minus f prime of 0 s here. So what is the Laplace of f prime in this case? It is s square Laplace of f, and over here what we have is 0, and then it is omega. Okay, so from here for f prime it is equal to Laplace of omega square sine omega t. Okay, so it is if we write Laplace of f double prime over here, it will be minus omega square Laplace of sine omega t. Okay, so it will be minus omega square Laplace of sine omega t, so which is same as the minus omega square Laplace of this f. So it is s square Laplace of f and minus omega. So from here, if I rearrange the terms, so it will be s square plus omega square Laplace of f is equal to omega, or in very quickly, Laplace of f is equal to omega over s square plus omega square, which is the same relation which we already know for the Laplace of sine omega t. So similarly, by the same manner, we can find the Laplace of cosine omega t. So in this way, we have found in another way how to find the Laplace of sine omega t and cosine omega